I'm presenting some of our results from deliverable D8.1, which was on the role of ocean mesoscale on hydroclimate and ocean extremes. I'll be presenting the part on ocean extremes, some of it. So it's how do EERIE models represent ocean extremes. So the data I used was the EERIE model data against observations at daily resolution from 1982 to 2014, regraded to quarter-degree resolution, and we clipped the latitudes from 50 south to 70 degrees north, and then removed all of the CIs. So the observational data set is the Ostia sea surface temperature satellite data, and then I used all of the EERIE models. These colors that you see on the left are the line colors that I will be using on the graphs. So let's start with defining what is a marine heatwave so that my results will be a bit more clear. A marine heatwave is a prolonged period of extremely warm water temperature. So if, for example, we take sea surface temperature SST at one location, like in this example, what we do is we first define a climatology seasonally varying so that everything above this climatology is considered an SST anomaly. And then we define an extreme threshold, which for us in this report was the 95th percentile. And everything above this extreme threshold is considered an SST extreme. So then, following the definition by Hobday et al., a marine heatwave event is when sea surface temperatures are above this extreme threshold for at least 5 days, with 2 days gap allowed. So this was, for example, a 6-day long event. And some characteristics of marine heatwaves are magnitude and intensity. So magnitude is the temperature of SST anomalies, so everything above the climatology, and the intensity relates to extremes, so above the extreme threshold. So the objective of the deliverable on my side was to assess how the models represent SST anomalies and marine heatwave characteristics. To study marine heatwaves, we differentiated between marine heatwaves on a fixed baseline, which means that we did not detrend, so we didn't try to remove the warming signal, and therefore we looked at the anomaly trends and how marine heatwave increased or decreased during this period of study. And we looked also at marine heatwaves on a detrended baseline. So here we're trying to study more so the variability, so we removed climate change signal, and we look at frequency, duration, magnitude, and area of marine heatwaves. So let's start with our regions, which we will be using throughout in our results. So we defined 5 regions in the Pacific. The equatorial Pacific is split in 2, Eastern Equatorial and Western Equatorial. And then we have 4 regions in the Atlantic, 3 in the Indian Ocean, and then the Mediterranean and the Southern Ocean. So for SST anomalies, we looked at the probability distribution function of SSTAs in each region and at a global level. Globally, what we see is that all models performed quite well. We have a very close match with IFS NEMO to Ostia, which is the black line. All the other models saw somewhat of longer tails, so more extreme anomalies, but still they're matching the observations quite well. 2 regions that stand out are the Southern Ocean, which is a highly dynamical area, and we can see how the higher resolution models are outperforming the lower resolution HEDGEM models. And as well, the Equatorial Pacific was a region of interest. Here we have a close match between ICON and the observations, and all the other models have varying degree of fidelity, with the lower resolution being, again, the worst performer. So now I will show you a very busy table where we look at the mismatch between these PDFs and of the models and of the observations. So we looked at how much of the area of one model was not explained by the Ostia observations. So we have all of our regions on the left, all of the models up here, and the global mean mismatch over here. So this is a lot. On the left, we have the mismatch of the SST anomalies distributions and on the right, the mismatch of the extremes distribution. So in general, before we focus on a few areas, I want to point out that for SST anomalies, the results were quite good. So we have very low mismatches between the models and observations, both regionally and global. For the extremes, we have a few areas of difficulty. For ICON, the worst mismatch was in the Eastern Equatorial Pacific with 27.8%. For IFS FASM, it was the Atlantic Equatorial with 22.7%. For IFS NEMO, it was the Indian North Subtropics with 22.3%. For HEDGEM High Resolution, it was the same region with 15%. The medium resolution HEDGEM had the North Pacific Subtropics, and the lower resolution, which had also the highest mismatch, was in the Western Equatorial Pacific with 29%. Then we look at marine heat waves on a fixed baseline. So we move on from the SST anomalies to marine heat waves. And what we're looking at here is the warming trend of the SST anomalies over the period of study. For observations, we had that between 1982 and 2014, Ostia had an increase of 0.45 degrees Celsius. ICON and IFS NEMO match this warming trend very well. And the other models are all overestimating to a certain extent, with, once again, the lower resolution HEDGEM being the worst performer per se. Similarly to this graph, we also look at the increase of marine heatwave days. So how many days there were globally in each model and in observations. And we have that the observed increase was 7 days. And here the models agree less. So ICON and IFS NEMO are still the best performers, but overestimating a bit. And the other models are overestimating quite a lot, especially, again, the lower resolution HEDGEM models. So now we look at these results. So global average marine heatwave days increase at each region. So similar table from before. We have Ostia on the left, all of our regions, and the models down here. So each square is what was the change in marine heatwave days at each region. And here I will show you which models performed best in each region. So we have in total that ICON was the best in 8 out of 15 regions, and HEDGEM's lower resolution was the worst in 10 out of 15 regions. So we have let's say, a good results on the high resolution models. Now let's move on to marine heat waves on the trended baseline. So we're looking at the trended results, so no climate change, hopefully, to the best of our capabilities. And we're looking at marine heat waves frequency. So the number of marine heat wave events that we have per grid cell, total and on average per year. So what stands out over here in the observations is in the Eastern Equatorial Pacific, we have very much lower number of events, so rarer. And this is very typical of this region due to ENSO. And this is not greatly represented by ICON and IFS FASM, whereas the other 4 models somewhat see this pattern of less events, but with not exactly, let's say, the same shape, so not exactly a perfect result. So if we take this map and look at that result on a regional level, what we see is in that most regions, the models are underestimating the number of events, which is quite coherent with literature. We see this with other models as well, except, as I said, in the Pacific Equatorial, ICON and IFS FASM are overestimating the number of events. And what goes hand in hand with marine heat waves frequency is marine heat waves duration. So similarly, as we expect less events over here, these events are also longer. So the 4 models over here, IFS NEMO and the 3 HEDGEMS models, see these longer, rare events, but IFS FASM and ICON don't. And we see similarly in the regions results that in all of the regions, the models are overestimating duration, except for the Eastern Equatorial Pacific, where ICAN and IFS FASM are not seeing these very long events. And we look next at the maximum magnitude of marine heatwave. So magnitude, as I said before, was the value of SST anomalies. So the values of these marine heatwaves above the climatology threshold. And we're looking at the maximum value any event had at each grid cell. And these are the biases. So ICAN minus Ostia and so on for all the other models. What we see for ICAN is that we have a very cold bias in the ENSO region and some hotspots in other places. IFS FASM also have a general cold bias in the equatorial Pacific, but we also see very strong warm biases at higher latitudes. IFS NEMO in general has a spread out colder bias, and the HEDGEMS models have, I say, less structured biases. So we see some hotspots in red and in cold. What stands out is mostly that in the lower resolution, we tend to have colder biases near the coast. And then we have this very strong hotspot of warm bias over here. And this is due to the fact that the lower resolution HEDGEM has a very strong ENSO signal, which is a bit shifted to the middle. So this is reflective of these very strong marine heat waves that are due to a stronger ENSO. So then we look at our final characteristic of marine heat wave, which is areas. So to study the area of marine heat waves, we had to switch from a Eulerian pinpoint approach to a more connected point of view. So we took our field of detected marine heat waves and we applied image processing. So we applied closing and opening, which is cleaning of the image, and then labeling, so that we switch from pinpoint marine heat waves to connected events, connected only in space, not in time, because we're just interested in the area. So what we find is these PDFs of area distributions. And these are very good results because in all the regions except one, and in the global results, the high resolution models are performing quite well at seeing the true area distributions with some degree of error, but the HEDGEM's lower resolution model is very, let's say, not great in all the regions and in the global as well. So it really struggles to see the real mean and the real distributions of the size. And then let's look at two specific regions, which are the Eastern Equatorial Pacific. And here we can see that ICAN and IFS FASM are not seeing this peak in area. And as I've said before, in the Eastern Equatorial Pacific, we tend to have very rare, very long, intense, and large marine heat waves. So ICAN and IFS FASM do not see this, but the other models do, with varying degrees of rightness. And in the Southern Ocean as well, we can really see how the higher resolution makes a difference in the performance of the models. So to conclude, what we looked at was SST anomalies and extremes thresholds. And we find that all the models perform quite well at reproducing the SST anomalies distribution and the extremes, but with the extremes, we have a little bit of difficulty in specific areas. And the lower resolution HEDGEMS models is the worst performer. For warming trends, ICAN and IFS NEMO perform very, very well. They align most closely with Ostia, whereas the other models have a little bit of higher warming responses. And once again, the lower resolution HEDGEMS is the worst performer overall. When it comes to marine heat waves characteristics, all the models perform quite well with varying degrees of fidelity. We find that the Equatorial Pacific region is problematic for ICAN and IFS FASM, and we know that this is due to the fact that ENSO is either not present or not well reproduced in these models, so it has a high impact in this region specifically. With that, thank you, and funding slide.
So my name is Mulalo. I'm also on Deep 8.1, the role of ocean mesoscale, imaging ocean, and hydroclimate scale extremes. I'm going to be looking at mesoscale convective systems. So what are mesoscale convective systems? These are typically classified as organized convective clusters of storm that expands to several hundred of kilometers and persists for several hours. They are very important for rainfall, redistribution of heat, moisture, as well as energy throughout the atmosphere. But there's also danger with the system in a sense that they produce extreme weather, such as damaging hail, lightning, as well as flash floods. Over Africa, we tend to find these systems over the tropics, over West Africa, as well as Southern Africa. But unlike other regions in Africa, Southern Africa hasn't received a lot of studies. And when it comes to mesoscale convective systems, this is partly due to lack of data in order to study these systems. So usually what you need to study the systems, you need high resolution observed data. That's from high resolution satellite. As you can see there, that's around 3 to 4 kilometers to about 10 kilometers. That's where we have seen a lot of studies coming. When it comes to model, general circulation models of 100 kilometers cannot really simulate these systems. Parameterized models of around 25 kilometers can have parameterized rainfall, but you need higher resolution when it comes to storm resolving models of around 4 kilometers to around 10 kilometers. That's when you start to be able to simulate these systems. So how do you identify mesoscale convective systems? Over the past few years, there's been a lot of tracking techniques that have been developed in order to simulate these systems, especially over the world. But here, what we have done, we have used one of the recently developed tracking algorithm called PyFlex Tracker from Feng et al. 2021. So over Southern Africa, what we have done, we have followed the same steps. We identify the cold cloud shield. And then from there, you link the detected cold cloud shield with a 50% overlap. So that's the cold cloud shield developing over time. And then you link that with the precipitation that comes with that cold cloud shield that has been detected. And then obviously with the cold cloud shield, it needs to have a certain area. And then with the precipitation, it needs to have a certain exit. So with the cold cloud shield, it needs to have an area of about 40,000 kilometers squared. And then we tend to keep that as a mesoscale convective systems. Rather than that, if it doesn't follow all those guidelines, you tend to discard it as just a cold cloud shield system. Obviously, when you tend to track these systems, there's other possible systems that you're gonna tend to track. For example, a tropical cyclone does also have a very cold cloud top, and it also tend to produce a lot of rainfall. A cold front over Southern Africa that tend to track south of Southern Africa, they tend to also produce a lot of rainfall. So the tracking algorithm tends to confuse that as a mesoscale convective system. So there is that process where you're gonna need to actually remove those systems from the observations. So when it comes to the data set used, especially with observation, we are using IMAGE rainfall data, and then you are also using brightness temperature data. So you're gonna use those two in observation in order to track those mesoscale convective systems. And then when it comes to the model, we only have one model that had the output from EERIE, which was the icon model in historic as well as future. So the model doesn't really produce a brightness temperature, doesn't simulate that, but it produces what we call a long wave radiation or outgoing long wave radiation, which is what we use in order to track these systems. Due to the conversion that we do, we convert this OLR into brightness temperature, and then we can just follow the similar systems or similar steps that we did in observation in order to track these mesoscale convective systems in higher resolution model. So when it comes to the results, we have focused on two subdomains where we are focused on the whole of Southern Africa, south of the 10 degrees south. That's just south of the equator. We focused on two subdomains, which is the one in blue and the one in red. The one in red is around the Mozambique Channel. which is over the east of Southern Africa, and then the one in blue is over the region what we call the Congo Air Boundary region. As you can see, the first one here, you're looking at the observation, and then you're looking at the icon model. This is the full track path of each tracked mesoscale convective systems for the austral summer season. So we are looking at from October to around March, and then we're looking at the historic period of 2000 until 2014. So we did a similar period in the observation as well as the icon model. When it comes to how the model identifies the hotspots, starting with the observation, we can see there's a hotspot of tracked mesoscale convective system over Madagascar, as well as northern part of Mozambique. There's also another secondary hotspot of southeast of Southern Africa or South Africa over there, just next to the Indian Ocean. There's also another hotspot over the Angola highlands inside the blue box, although it's not as prominent as in Madagascar as well as northern Mozambique. And then when it comes to the icon, we see that there is a very prominent hotspot, which is over inside the blue box, which is along the Mozambique Channel, extending down to northern parts of Namibia. That's in the west parts of Southern Africa. And then obviously over the east, it is similar to what is actually simulated in the observation, where you have a hotspot over Madagascar as well as northern Mozambique there. So we looked at some characteristics of mesoscale convective systems. Here we are looking at the two boxes that we showed in the previous slides, the red box, which is the Mozambique Channel, and the blue box, which is the Congo Air Boundary region. For the first one, we're looking at the seasonal cycle. So we're looking at the mean number of mesoscale convective systems per season. We're looking at both the observation as well as the model. So with the observation for the blue box over the western part of Southern Africa, you're looking at looking at both regions, you're looking at the model actually simulating the mesoscale convective seasonal cycle well, in a sense that the count might be differing when it comes to especially overland in the eastern box, that is the one in blue, in the western box, the one in blue, where you tend to have a model getting very high number of mean number of system per month as compared to what is actually observed on the ground. But when you go to the red box, which is the Mozambique Channel, you look at for each month, there is a comparable number of detected systems for both observation as well as the icon model. And it is actually interesting that the peak when it comes to where they usually peak in each month, both the model and the observation tend to get December, January, Feb as the months where you get more of this system, just average within those two boxes. And then from the two here below, you're looking at the duration and the percentage, the how long does these systems tend to last. You're looking at overland, which is over the west. This is the Angola highlands, the Congo Air Boundary region, and then see you're looking at the Mozambique Channel there. It is interesting that over the domain, which is ocean dominated, see there, which is the Mozambique Channel, the icon model actually does very well when compared to the observation, because you're looking at the storm, the percentage where the storm is actually tend to be distributed. You have the peak in 12 to 14, 15 to 17 hours, where most of the storms tend to last these hours. And then obviously you have a lot of storms that actually extend for prolonged period of over 24 hours. So that's a storm lasting for more than a day. And then for the for B there, which is the Angola highlands, and then the Mozambique, the Congo Air Boundary region rather, you have obviously for peak hours of 12 to 14, 15 to 17, it's comparable. But for storms that are long lasting more than a day, the model tends to have more of such storms, whereas it is not actually truly what is being observed. So we move to one of the most important things of mesoscale convective systems, which is their rainfall contribution. So here we started with the observation. So you can see that the contribution peaks at over 50% of contribution of rainfall, with the Mozambique Channel coming down to Madagascar and most part of Mozambique, where this system tends to contribute to over 50% of rainfall. And then you also go to the southeast of South Africa, where they actually also play a major role in the seasonal rainfall over there. But how does this compare with the ICON model? Well, when it comes to the model, the contribution of this system is similar over the east, where you have a high contributing to over 50% of the seasonal rainfall, of the daily rainfall for that season, for the austral summer season. But you look at the east, the west, rather the west of Southern Africa, the region around the blue box going down to northern parts of Namibia, there seems to be a high contribution of these systems, whereas this is not what is truly observed by the contribution of the observation of observed mesoscale convective systems as compared to what we're seeing here in ICON. So that's actually one thing to take note of. Well, we went on further to actually just look at this rainfall evaluation of the ICON model over Southern Africa, because this is important, since when you're tracking these mesoscale convective systems, you actually tend to use rainfall, especially light rainfall of 2 millimeter, as well as heavy rainfall of over 10 millimeter, in order to identify these systems, as well as their rainfall contribution. So we looked at ICON when it comes to looking at rainfall in ICON as well as IMAGE over Southern Africa. So you can see most places there is a wet bias when it comes to ICON rainfall. That means that you tend to get more places getting more rainfall from ICON as compared to what is actually observed. We did the same with heavy rain days, which is rainfall which is over 10 millimeter during the same austral summer month. The heavy rain days of rainfall greater than 10 millimeter is actually important, because when it comes to PyFlex tracker, it uses this in order to as one of the links, or when it comes to tracking these mesoscale convective systems. So you can see there's a positive bias in terms of the number of heavy rain days in the austral summer period over central parts of South Africa, going there to the Atlantic, where you have there over the ocean of next to Angola, coming down to northern parts of Namibia. So this is very, very interesting, because this is the same area that we saw that large contribution from ICON when it comes to MSC rainfall as compared to what was observed in the observations. So we went on further to try to understand what could be causing more MSC occurrence, especially in the West. So we found that there is that rainfall as well as heavy rainfall bias over the West. So some of these events could be attributed to mesoscale convective systems. So we look at the SST bias. Clearly, there is a very, very warm SST bias over the Benguela current region, which is a region that is important for rainfall. This bias could be actually, this SST bias could be actually contributing to more MCSs that are actually observed or that are actually simulated over the western part of Southern Africa in ICON, rather than what is actually observed. So there's still more and further that we're still doing when it comes to these systems. We're still looking at how they're gonna change going into the future. That's the work that we are currently working on at the moment. So for this and for today, I'll leave this here. And then here we have the funding slide. Thank you.
Hi, I'm Amber, as Thomas said, and I'm just going to present our contribution to D8.1, which was focusing on atmospheric rivers. Just a bit of background about what atmospheric rivers are. They are long, narrow corridors of very strong vertically integrated water vapor transport, and they are situated in the mid-latitudes, transporting water vapor from the tropics towards the poles. They are both a very important source of moisture for many regions, and also a very big source of rainfall extremes. And specifically for us, recently, actually, last week, we had a very unique case where we had two atmospheric rivers that made landfall on the southwestern Cape of South Africa and resulted in very, very, very heavy rainfall and flooding, which caused a lot of damage to a lot of infrastructure, specifically in the transport sector. But yeah, it was very, very bad for us. And this was quite a unique case, as I said, because we had two atmospheric rivers and a cold front as well, so it was just feeding in a lot of extra moisture. So yeah, this kind of highlights the critical side of them where they can contribute to rainfall extremes. But then on the flip side, they are also very important for many regions for rainfall. So it's very, very important for us to understand them. So this has kind of been what I've been doing for the last few years, and now kind of expanding this to look into the model side of things. So just a bit on why it's important to study atmospheric rivers in models. So they're very well studied in reanalysis data sets like ERA5. And because they're closely linked to flooding and extreme rainfall, it's very important that climate models can represent them accurately. And a lot of large-scale climate models generally tend to capture the broad seasonal cycles and moisture transport patterns associated with ARs, but they can often struggle with the fine-scale structure of the systems. This is mainly because global climate models operate at a relatively coarse spatial structure or spatial resolution. So it's quite nice for us now with EERIE, we've got higher resolution models. But yeah, previous studies have shown that higher resolution models tend to represent atmospheric river related precipitation a lot more realistically, particularly in situations where we've got complex topography and ocean eddies. So one of the key motivations for this work has just been to understand how atmospheric rivers are represented in models compared to observations, and then also how the resolution of models impacts our atmospheric river representation. So just a bit of background on how atmospheric rivers are traditionally detected, because we've chosen to go a slightly different route here. So traditionally, they are detected using a thresholding-based method, which has been great for many studies, but the problem here is that they can often be highly sensitive to changes in atmospheric moisture, and this becomes a bit problematic when we're comparing different climates or different model simulations. So we wanted to kind of avoid this. So what we've chosen to do is use an image processing detection method called IPART, and rather than relying purely on magnitude thresholds, IPART uses an image processing based detection method, as I said, which uses top hat reconstruction, which essentially detects bright objects on a dark background. So for us, our bright object is going to be the atmospheric river, and that is from the dark background and then detected as an individual feature. And then it's able to actually track these features or link features together to form one system and track it through space and time. There are a few methods that use image processing, but we found this one was the best option for us. And then we have now validated this using ERA5 reanalysis data and developed a climatology for the Southern Hemisphere from 1979 to 2023. And we've kind of used this as like a base for all of our comparisons. This is also a very nice thing for us, as I said, going into using different models, it's going to be a very good baseline to also have a bit of a more robust detection method. So yeah, we've done quite a lot of stringent sensitivity testing just to make sure that the detection algorithm works very well for our region, because when translating it, it was developed for the Northern Hemisphere, and when we translated it to the Southern Hemisphere, it didn't perform super well. So we've done quite a lot of regional tuning, and we're quite happy with where we are now. We went for a sort of middle ground approach and found an optimal set of parameters to use. And what we found from here, as I said, we developed a South Atlantic and Southern Hemisphere climatology for 1979 to 2023 using ERA5 reanalysis, and then we have replicated this in the HADGEM. Up till now, we've done HADGEM medium resolution, but we're going to be doing this for the high resolution and for the low resolution as well. And we found that HADGEM also captured the seasonal cycle pretty well, but it was picking up too many atmospheric rivers with very short lifespans, and they also tended to have a lot stronger IBT or higher IBT values. So we didn't really understand what was going on here. But as I said, it wasn't it was pretty good at picking up the overall seasonal cycle. We found using HydGem that the seasonal atmospheric river climatology reveals a migration in atmospheric rivers, as we saw with our ERA 5 dataset. So during summer, atmospheric rivers are concentrated further south of southern Africa. So a lot of them tend to miss us and don't really produce a lot of
Amber,
rainfall.
I
Yes,
don't see your screen anymore. You may have lost screen sharing.
really. So as I was saying, I'll just start this slide again. As with ERA 5, we saw in summer, we saw a lot of the atmospheric rivers are concentrated further south, so a lot of them are missing us in South Africa and not contributing to rainfall. But then we saw a bit of a shift towards the equator in the shoulder seasons, and specifically in winter, which is when we receive most of our atmospheric river related rainfall. And yeah, this was quite reassuring to us that the models were representing the seasonal cycle of atmospheric rivers quite well. There we go. And I've just kind of summarized what we've seen in the two different observations and the models. And we intend to replicate this for the high resolution and low resolution as well. And we're hoping with the higher resolution, it's slightly better and closer to what we see in observations. And then just a bit of a word on why resolution matters. So resolution has a massive influence on the structure of atmospheric rivers because they're filamentary systems. So it's very important that they are picked up correctly. In the high resolution simulations, which we've done very limited periods of, we've seen atmospheric rivers appear as narrow, well-defined filaments. That figure on top there you can see is in the high resolution HydGem. And then underneath that, we've got the medium resolution. Obviously, two different time steps, but you can just see the general structure of the atmospheric rivers. And as the resolution just decreases, the systems become a bit broader and smoother with a noticeable loss of detail in the structure of them. But importantly, as I said previously, the large-scale seasonal patterns tend to remain relatively robust across the different model resolutions. And then, yeah, just a bit more on the benefits of using high-resolution models. So they better capture the filamentary structure, as I said, the intensity as well, and then their interactions with storms and, for us, cut-off flows and cold fronts, and then also hopefully the contribution to rainfall, which is one of our next steps that we're going to be analyzing. So just to summarize, this work demonstrates that atmospheric river detection methodology and model resolution plays a big role in the climatology that's produced. And through regional tuning, we've managed to get an image processing algorithm to successfully work for the Southern Hemisphere. And the initial things we've seen with HydGem is that it successfully captures the large-scale atmospheric river behavior. And we're hoping that the high resolution will be even better than the medium resolution because the model resolution does play a big role. And yeah, the differences are very important because they ultimately are going to affect the downstream impacts for us in Southern Africa and for other areas in the Southern Hemisphere, such as precipitation and the risk of flooding. Yeah, thank you.